Hello, and in this video I just want to do a quick reminder of phasors, what they are and how they work and how you can use them. So first of all, what is a phasor? Well, it is a complex number which represents the amplitude and the phase, but not the frequency, of a sinusoidal oscillation. If I have a waveform which has the form A0 times cosine omega t plus theta, then I could represent that waveform by a complex number with a magnitude, that's a distance from the origin of A0, and a phase, that's an angle to the real axis of theta. So that would be represented by a complex number there, where this is the imaginary axis and this is the real axis. And the distance from the origin would be A0, and this angle there would be theta. And they're very useful in adding up sine waves of different amplitudes and different phases, but the same frequency. And when we're applying Kirchhoff's current law for doing nodal analysis in circuits in which the sources are sinusoidal oscillations, phasors are extremely useful. A few quick questions to do some examples. In this case, the dotted blue signal represents a reference. It's the waveform represented by a phasor of 1. So a magnitude of 1 and a phase angle of 0, it would just be a distance 1 along the real axis there. And that represents just cosine omega t. That's the reference phasor. If that was R, that's y up there, a phasor representing y of t. So that's just a cosine wave plotted like any other cosine wave like this. Now, the waveform that I'm trying to represent in phasor form is this solid blue one here. And I need to work out if the amplitude and the phase of this one. Well, I can see that this is 90 degrees ahead of this one. It starts at 0. It has its minimum value a quarter of a cycle before the reference phasor. Its maximum value is a quarter of a cycle before the reference phasor as well. A quarter of a cycle is 90 degrees, so the phasor representing this blue waveform is going to be 90 degrees away from the real axis. And it's going to be 90 degrees straight up. That's because it is ahead of the reference waveform. Things happen first on this blue waveform. And that means that the angle is positive. So this blue waveform here would be represented by a phasor along the positive imaginary axis. And the amplitude looks like it's about 1.6. So I would represent that blue oscillation, the solid blue oscillation, with a phasor something around 1.6 J, which I could also write as 1.6 times e to the power of j pi over 2 in radians, or 90 degrees in degrees. The reason we're using phasors is that they make it very easy to add together sinusoidal oscillations of different amplitudes and different phases. Take this example. I've got two oscillations here. They're at the same frequency, so I can use phasors. This first one here, I would represent by a phasor of amplitude 1, but phase angle pi over 2 in radians. So that would be a phasor along the positive imaginary axis, because its angle is plus pi over 2. So that would be there at J. This phasor has a magnitude of 3 times the square root of 2, and its angle is positive pi over 4. So that would be along this line here somewhere, and its magnitude is 3 times the square root of 2. So that's going to be somewhere around here, where this distance is 3 root 2, and this angle here is pi over 4 radians, or 45 degrees. And I can work out what the sum of these two sinusoidal oscillations is by adding up the two phasors. That's the real power of phasors. That I can do by expressing this second phasor here in terms of its real and imaginary parts. This phasor is going to have a real part of, well, considering this right-angled triangle, the length of this side, which is the real component of this phasor, is going to be 3 root 2 times cosine of 45 degrees. And the imaginary part of this phasor, that's the length of this side of the triangle, is j times 3 root 2 times cosine of 45 degrees. Well, cosine of 45 degrees is 1 over root 2. So this is in fact just equal to 3 plus 3j. That's this phasor here. If I add this phasor, I would end up with 3 plus 4j. So that must be the phasor which represents the sum of these two cosine waves. If I want then to work out what cosine wave is represented by this phasor, I need to work out the magnitude and the phase of this phasor. Well, Argand diagram to the rescue again. If I do this and note that that is where my resultant phasor would be on the Argand diagram, it has a real component of 3 and an imaginary component of 4, then it's going to be at that point there. This is a very famous right-angled triangle. Its hypotenuse is of length 5. If you don't recognize that, you can quickly get it by just applying Pythagoras to this triangle. And this angle here is going to be the inverse tangent of 4 over 3 in this case. So that phasor there is going to be 5 times e to the power of j, and the phase angle is the inverse tangent of 4 over 3. That is the phasor which represents the oscillation with amplitude 5 and phase angle tan to the power of -1 of 4 over 3. So that would be the sum of those two cosine waves. Now you may be wondering why this works. Well, it works because we can represent a complex number, say a e to the j beta, in terms of a cosine of the phase term beta and the sine of the term beta as well. Very useful, famous formula. E to the j beta equals cosine beta plus j sine beta. Now, if I let beta be omega t plus theta, I would have a e to the j omega t plus theta is a times cosine omega t plus theta plus j times a sine omega t plus theta. So if I take the real part of this, well, the real part of the right-hand side here is just this cosine term here, because this term is completely imaginary. So I can represent my sinusoidal oscillation in terms of the real part of a complex number, which I could write like this. Or a e to the j theta times e to the j omega t. If I had another cosine wave, say b times cosine omega t plus phi. That would be the real part of b e to the j psi, e to the j omega t. And if I wanted to add up these two cosine waves, well, if I just add up the real part of this expression with the real part of this expression, I must get the real part of this plus this. So the sum of these two cosine waves is going to be the real part of this complex expression plus the real part of this complex expression. If I add up two complex numbers, the real part of the sum must be the sum of the real parts of the complex numbers. So that's just going to be, if I do a bit of simplification and remove the common factor of e to the j omega t, a times e to the j theta plus b times e to the j psi times e to the j omega t. But this, as we've seen, is the form of a cosine wave, which is going to have an amplitude given by the amplitude of this term, and a phase given by the phase of this term. So all I have to do is work out the amplitude of this and the phase of this. That might be, for example, equal to c e to the j psi times e to the j omega 2. Just adding up those two complex numbers to give me this complex number here. That is a cosine wave c cosine omega t plus psi. So I've added up my two cosine waves here, and I've produced an output cosine wave here with a different amplitude and a different phase. And the amplitude and phase of this sum is given by adding up these two complex representations, or phasors, representing these two cosine waves. There's a demo on the website so that you can play around with this. It looks like this. Here we've got a oscillation with a phasor of 1, so it has an amplitude of 1 and a phase angle of 0. Here is another one. We're adding them together and we're producing this output result. If we were to move this one to there, then the sum of these two complex numbers, these two phasors, would be a phasor at this point here, with a length of √2 and a phase angle of 45. And that results in an oscillation with an amplitude of √2 and an angle which is 45 degrees out of phase with both of its inputs. If I move this one to here, then I get the case where I'm adding a phasor of +1 to a phasor of -1, and the result is 0. In terms of the time domain waveforms, I'm adding a cosine wave to a cosine wave which has its exact opposite phase, and it cancels out at every point, leading me to have nothing. That's all I have time for in this one. Next time I want to carry on and say a few more things about the use of phasors.